Hello friends, so today we are going to solve few questions, and these questions are from the year 1986, 1987, 1988 and 1989. From 1986 we are having one question. From 1987 we are also having one. From 1988 we are having two, and from 1989 we are having three questions. So in total we are having 7 questions. Okay, so let's start with the first question, and it states that it was asked in the year 1989, and it states that a modified Young's double slit experiment, a monochromatic uniform and parallel beam of light of wavelength 6000 angstrom and intensity 10 by pi Weber per meter square is incident normally on two apertures A and B of radii 0.001 meters and 0.002 meters respectively, a perfect transparent film of thickness 2000 angstrom and refractive index 1.5 for a wavelength of 6000 angstrom is placed in front of aperture A. See figure. Calculate the power received at a focal spot F of the lens. The lens is symmetrically placed with respect to the apertures. Assume that 10% of the power received by each aperture goes in the original direction and is brought to the focal spot. So we have this is a figure, and in this figure we have two apertures, A as well as B, and in front of A there is a thin film, and this entire ray which are passing from A and B with the help of this lens is being focused at F, and it is said that only 10% of the power received by each aperture goes in the original direction. Okay. So in this case we have to find out what will be the power received by, or we can say power received at point F. So we are given that, first of all, let's find out what will be the power transmitted through each aperture, A as well as B. Power transmitted through each aperture. And we can write that formula. Suppose that power is given as P, then this P will be equal to intensity multiplied by area, and we can write this formula for both the apertures. You can say for aperture A, PA will be equal to the power received, that is our intensity, is 10 by pi. So this lever comes as intensity received by A and area of A. Intensity received by A is our 10 upon pi, and its area will be equal to pi RA square. We substitute a value, we get power received power transmitted through A, which is equal to PA, will be equal to 10 upon pi multiplied by pi, and we have our RA is our 0.001 and whole square. So this will be coming as pi goes with pi, so we can write it as 10 into 10 raised to the power minus 6, which comes as 10 raised to the power minus 5 watts. Similarly, we can write for aperture B, so we have PB is equal to intensity B, area of B, which comes as 10 upon pi multiplied by pi RB square. So this gives us power of B is equal to intensity is our 10 upon pi multiplied by pi, and the radius is given as 0.002 whole square. Here pi goes with pi, and this we are left with 10 into this will be equal to our 2 to the 4 into 10 to the power minus 6, giving us 4 into 10 to the power minus 5 watts. So these are the transmitted powers through the apertures, and it is said that only 10% of the power is reaching the focal point. You can say power reaching the focal spot. And it is said that this is only 10%. So we can write for aperture A, let us call that as PA prime, that will equal 10% of PA. So this gives us PA was 10 raised to the power minus 5. So this gives us 10 raised to the power minus 6 watts. Similarly, we have for PB, that is our PB prime, will be equal to 10% of this, which is 4 into 10 raised to the power minus 5. This gives us, this goes by 0, and we are left with 4 into 10 raised to the power minus 6 watts. And there is a, you can say, transparent sheet that is in front of the aperture A. So we have to find out what will be the effect of transparent film, and this transparent film is going to introduce a phase difference. You can say effect of transparent film, and that effect will be phase difference. And we can write that as delta x is equal to mu minus 1 and multiply by t. Mu is the refractive index, which is given as 1.5, minus 1, t is the thickness, which is given as 2000 angstrom, 2 raised to the power minus 7. So this comes as 10 raised to the power minus 7 meters. So therefore, we can write that the phase difference phi, or rather we can say delta phi, will be equal to 2 pi, and we have this 6 into 10 to the power minus 7, which was the wavelength, and this comes as, sorry, I missed one part, and multiply by 10 to the power minus 7. So this gives us pi by 3, because this goes with this, 2 goes by 3, so I left with the phase difference of pi by 3, or we can simply call it as 60 degree. So therefore, the resultant power at the focal spot, at focal spot, that is our P, will be equal to PA prime plus PB prime plus twice PA prime PB prime, and we have cos of the phase difference. Now we can easily substitute the value. PA prime is our 10 to the power minus 6, PB prime is our 4 into 10 to the power minus 6 plus 2, and this comes as 10 to the power minus 6 multiplied by 4 into 10 to the power minus 6, and we have cos of pi by 3. So therefore, we can write this will be equal to, this come 4 plus 5 minus 6 plus this comes as 2 into, this will be our 2 into 10 to the power minus 6, and cos of this will be coming as 1 by 2. So this 2 goes with 2, and we get this as 5 plus 2, 7. So we can write this will be equal to 7 into 10 to the power minus 6 watts. Yes, so this completes the first question. In the second question, it was asked in the year 1989, and it states that an astronomical telescope has an angular magnification of magnitude 5 for far objects. The separation between the objective and the eyepiece is 36 centimeter, and the final image is formed at infinity. The focal length f0 of the objective lens of the objective and the focal length fe of the eyepiece are. So in this case, we are going to find out what will be the focal length of the eyepiece and the objective, which is formed at the infinity. So in this case, we can use the formula, and which gives us the direct relationship between the solution. So here we have to keep in mind that the angular magnification is given to us as 5, and based on this angular magnification, we are going to solve it for the solution. Okay, so let's start from the given things which are given to us, and it states that the angular magnification is our 5, and we are given angular magnification which is given to us as 5. Let us suppose that is m, and this is equal to 5. Okay. And separation between the two, that is objective and eyepiece, is, that is our L, is 36 centimeters. This is separation between objective and eyepiece, it is denoted as L, and this is equal to our 36 centimeters. And we already know that for in case of normal adjustment of the astronomical telescope, L is equal to F0 plus Fe. We can write that the final image is as formed at infinity. Okay. We can say that final image is formed at infinity, so which basically means that normal adjustment. Normal adjustment. And under normal adjustment, our L is equal to F0 plus Fe. For normal adjustment, we have our L is equal to focal length of objective plus focal length of the eyepiece. And also the magnification, same for the normal adjustment, the magnification, that is our M, it is given as minus F0 upon Fe. And for its only magnitude consideration, we can write that our M will be equal to F0 plus F0 upon Fe. It is given as 5, therefore we can write that our 5 is equal to F0 upon Fe, which gives us F0 will be equal to 5 times Fe. And we are going to substitute this equation into the equation of the L, which states that our L is equal to F0 plus Fe. Length is given to us, and that is given as 36, will be equal to, it comes as 5 times Fe plus Fe, and this gives us that our Fe is equal to 6 centimeters. If Fe is 6 centimeter, therefore our Fo, which is 5 times Fe, it gives us that our Fo will be equal to 30 centimeters. So Fe is our 6 and Fo is our 30. So option number D is the correct one. Option D is correct. We come to the next question, and next question was asked in the year 1989, and it states that a beam of light consisting red, green and blue colors is incident on a right angle prism. The refractive indexes of the material of the prism for the above red, green and blue wavelengths are 1.39, 1.44 and 1.47 respectively. Then the prism will, so basically in this option it is given that which of the three colors will be separated or none will be separated. Okay. So this is a prism, it is a right angle prism, angle of 45 is there, as well as this will be also our 45. So we are given the refractive index for the red, green and blue with respect to the prism. So we can say refractive index for red is our 1.39, refractive index for our green is 1.44, and refractive index for blue is our 1.47. And as it is a right angle prism, so it means all the light is incident only at one face, that is only the perpendicular face. So let us call this as A, B and C. Okay. And here for the segregation of the color either red or green or blue, we have to find out what will be the you can say with respect to the critical angle or total internal reflection. So you can say that for total internal reflection, we know that the sine of theta c, which is a critical angle, is equal to 1 upon mu. So basically it means that higher the value of mu, smaller will be our critical angle. Higher mu means smaller is our critical angle. Therefore, we can write that the total internal reflection, or we can say light that suffer the total internal reflection, you can say light will suffer total internal reflection if the angle of incidence inside the prism is greater than the critical angle, is greater than the critical angle, which is nothing but our theta c. So from the refractive indexes that are given, if you make a comparison between them, we can say that the refractive index of the blue is greater than the refractive index of green is greater than the refractive index of red. Okay. So therefore, we can write based on this sequence, we can say the critical angle for blue will be less than critical angle for green, which will be further less than critical angle for red. So it means red is having the highest critical angle, and blue is having the smallest one. Smallest critical angle. And we can say that for the internal surface of the prism, the angle of incidence is such that the total internal reflections only takes place for green and blue light. You can say that the angle of incidence is such that total internal reflection occurs for green and blue, not for red. So it means red will be separated. Red will be separated. So therefore the option number A is the correct option. Option A is correct. We come to the next question, and here it was asked in the year 1988, and it states that a parallel beam of light traveling the water, refractive index 4/3, is refracted by a spherical air bubble of radius 2 mm situated in water. Assuming the light rays to be paraxial, we have to find out two things. Find the position of the image due to refraction at the first surface and the position of the final image, and draw a ray diagram showing the position of both the images. So here we are given that we are having a, you can say, a air bubble is inside the water, and the refractive index of the air bubble is refracted by the spherical air bubble. So here the refractive index of the water is given as 4/3, and the radius of the, you can say, air bubble is given as 2 millimeter. So in this case we are given that we have a refractive index of water that is about 4/3, and we are given that refractive index, because it is air bubble, so refractive index of air which is inside the bubble will be over 𝜇2. So we can write it as 𝜇2, that is air inside the bubble. Air inside the bubble, its value will equal to 1, and as the incident rays are paraxial, so object will be at infinity. Incident rays are paraxial, so it means that object is at infinity, which gives us that u is equal to infinity, and the ray is going to refract from a water which is a denser medium to the air which is a rarer medium. You can see the light first refracts, because it is going to have two refractions. So first time the light first refracts from water which is of a denser medium to air which is our rarer medium. Medium at the bubble surface. Okay. at the bubble surface. So this is when the light is going to reflect the first time, and we have to find out the image due to first refraction and the final position of the image after the second refraction. So these are the two things which are supposed to find out. So let us consider our first refraction. And we can use the formula that our 𝜇2 upon V minus 𝜇1 upon U is equal to 𝜇2 minus 𝜇1 upon R. And here R, because the center of curvature will be curved towards the incident light, so therefore we can substitute all these values and we can say that 𝜇2 is our 1. Yeah. So we get this as 1 upon V minus say 4 upon 3 times infinity is equal to 1 upon 1 minus 4 by 3 and divided by 2, and this gives us that our V, which is the position of the image, will be equal to minus 6 millimeters. And so you can say the first image will be formed 6 millimeter to the left of the first surface. You can see the first image is formed 6 millimeter to the left of first surface of first surface, and here radius is given as 2 millimeter. Okay. Next we come to the second refraction, that is at the opposite surface. Second refraction, or we can say at opposite surface. So here now the first image is going to act as a virtual object. First image acts as a virtual image. Therefore, we can write that object distance for second refraction, object distance for secondary refraction will be equal to minus, and this comes as 2 plus 6, which is our minus 8 mm. And once again, now the light rays will be moving from air to water. Now the light rays are moving from air with mu as 1, and it is a rarer medium, to water with mu as 4 by 3, and that is our denser medium. So we can use the same formula. We can write that our u3 upon v prime minus mu2 upon it is our u prime is equal to mu3 mu2 divided by r prime. Mu2 is our 1 and mu3 is our water. Okay, here should be mu3 and here should be 2. So you substitute, we get this as 4 by 3 v prime minus, this is 1 upon minus of 8, this gives us that 4 by 3 minus 1, 4 by 3 minus 1 and divided by minus of 2. This gives us that our v prime is approximately equal to minus 4.57 mm. So we can say the final image is located at 4.57 to the left of the second surface. Final image is located at left of the 4.57 mm to the left of second surface. Left of second surface. And now we can draw the figure, that is our part B, which were asked for. And in this case, let us say that our I is virtual image from first surface and I prime is the single prime. I prime is the virtual image from second surface. And we have a spherical surface. So let us draw a spherical surface, air bubble rather. So this is spherical and this is our principal axis passing through the center. This is our center and the rays are coming parallel. It is a paraxial. So rays will be, suppose this is one of the ray and the second ray, both are our paraxial. And we have this as a normal here and it will bend something like this, and on the bottom side also we are going to have this as normal and it will bend something like this, and if we extend it backwards, so this will be the image formed, and this is our eye because of the first surface. And at the second surface, so this is normal and here this is normal. So once again it is going to bend something like this, and here also it is going to bend. Sorry. Okay. Let me draw the normal again. So this will be our normal, and now we can just plot the bend like this, and if we extend them backwards, they will be meeting somewhere here. So this will be our second image because of the second surface, that is our I prime. And all these normal, if figured down correctly, should be meeting at the same point. Okay. So this will be our, and this is our, so this was our part B, and the object is coming from infinity, and around that we were having a water whose refractive index is given as 4/3. Inside it is air, so refractive index will be equal to 1. And this completes the question. We come to the next part, next question rather. And here it was asked in the year 1988, and the question is, two coherent monochromatic light beams of intensity I and 4I are superimposed. The maxima and minima possible intensities of the resulting beam are. So this is based directly on the formula itself. We know that the resultant is given by I1 plus I2 plus twice I1 I2 cos of phi, where phi is the phase difference between the waves. So we have intensity because of the first beam. So first beam intensity is I1, and we have this is second beam. Second beam intensity is our I2, magnitude is given as I, and this is I2, and its magnitude is given as, or value is given as 4I. And the resulting intensity that is our I resultant will be equal to I1 plus I2 plus 2 square root of I1 I2 cos of phi. And we have to find out the maximum and minimum possible intensities. So maximum and minimum means constructive and destructive interference. Constructive means maximum intensity, then cos of phi will equal to plus 1. Destructive means minimum, cos of phi will be equal to minus of 1. So we can say that max intensity, which is our constructive interference, this tells that the cos of phi should be equal to plus 1, and then we have minimum intensity, so which means destructive interference, this gives us that our cos of phi is equal to minus of 1. So let us find out our maximum intensity. That is our I max will be equal to I1 plus I2 plus twice I1 plus I2 cos of phi, in this case is equal to 1. We substitute the values, we will get I plus 4I plus, this comes as 2 square root of I multiplied by 4I, and this gives us that our maximum intensity, our I max, is equal to 9 times I. We find out now minimum intensity, that I minimum will be once again I1 plus I2 cos of I is minus 1, so this comes minus of I1 and I2. So this will be I plus 4I minus twice I times 4 times I. So giving us I minimum is equal to, this will be coming as I. So this is our maximum and minimum intensity. So the option 9 and I is the correct one. So option C is correct. Option C is correct. We come to the next question. Here it was asked in the 1987, and it states that a right angle prism is to be made by selecting a proper material and angles A and B, where B is less than or equal to A as shown in figure. It is desired that the ray of light incident on face AB emerges parallel to the incident direction after two internal reflections. Okay, so it is desired for this condition. There are two questions that was asked in it. First one states that what should be the minimum refractive index mu for this to be possible, and part B, it states that for mu is equal to 5/3, is it possible to achieve this with the angle B equal to 30 degree. So this is a given figure, a right angle triangle with C is a 90 degree, and it is desired that incident ray, which is perpendicular to AB and falling at a certain angle on the face AC, suffers internal reflection twice, total internal reflection, and it is desired that it should be following the parallel path with respect to the incident ray. So this is our incident and this is our refracted as well as reflected. And okay, so let us call this as point as P and this point as Q, and we can draw this is our incident angle, and here also we can say that the angle of incidence is this one. So we have two angle of incidence because there are two internal reflections, okay, and both are internally. So we can say that at point P, the angle of incidence, let me draw it clearly. So this is your first angle of incidence, let us call that as IA, and this is second one, let us call this as IB. So the angle of incidence, that is our IA, will be equal to angle A, and at point Q, so this is point P and this is point Q, you can say at Q the angle of incidence, that is our IB, will be equal to B, and it is given that B is less than equal to A. So we are given that our B is less than equal to A, and based on this we can say that our IB is less than equal to IA. So in this case the total internal reflection, if the total internal reflection satisfy the smaller angle of incident, that is IB, then it is going to automatically satisfy for the larger angle of IA. It means we are only going to find out that for total internal reflection with respect to angle IB, because angle IB is smaller than angle IA. If total internal reflection condition satisfy for IB, it will be automatically satisfying for IA. So we have to remember this, that if total internal reflection satisfies for smaller angle is our IB, then it automatically satisfy for larger angle, that is our IA. Satisfy for larger angle, which is our IA. So we are going to check only for angle IB. You can say that total internal reflection at B is to be checked. And because the prism is 90 degree at C, so therefore we can say that angle A plus angle B will be equal to 90 degree. Okay. And the maximum possible value of B is our 45. Maximum possible value of B is equal to 45, because under this condition only is our 45, because we have to take care of the condition that the B is less than or equal to A. So the only possible maximum possible value that angle B can hold is that B can be of 45. If B is not 45 or becomes like 46, it becomes greater than A. So I have to take care of this condition. So it means that maximum possible value of is 45. So if the total internal reflection condition is satisfied at 45 degree, then it is all satisfied for all values of B as well as A. So you can see from here that if total internal reflection condition is satisfied for B is equal to 45, then this total internal reflection is satisfied for all B and A. And the condition for total internal reflection at B, condition for total internal reflection at B is that our incident angle of B should be greater than or equal to the critical angle, that is our theta C. Or we can say that our 45 degree should be greater than or equal to theta C. And from here we can write our sine of 45 degree should be greater than or equal to sine of theta c, okay, and sine of 45 is 1 by root 2, and we also know that we can write that sine of 45 is equal to 1 by square root of 2, and sine of theta c is equal to 1 upon the refractive index. So we substitute the values, we get this as 1 upon square root of 2 is greater than 1 upon mu, and from here we get that mu is greater than equal to square root of 2, and which is approximately our 1.414. So the minimum refractive index which is possible can write minimum refractive index must be 1.414, and so this was asked in the first part, okay, possible value of the minimum refractive index. And we come to the part B. In part B, we are given the refractive index as 5 by 3. A refractive index is our 5 by 3, and this is our close to 1.666, and we already wrote that our sine of critical angle is equal to 1 upon the refractive index, sorry, it is mu. So this gives us 3 by 5, which is equal to 0.6. So theta c, that is critical angle, will be equal to sine inverse of 0.6, and approximately that will be equal to our 37 degree. And it is said that the angle B is for 30 degree. We are given that our B is our 30 degree. So our incident angle B will be equal to 30 degree. And since the prism angle is right angle, so therefore we can write that our incident angle at A will be equal to 90 minus 30, which gives us 60 degree. And if you make a comparison between angle IA and critical angle, we can see that angle IA is greater than our 37 degree. We can say that our IA, which is 60 degree, is greater than our critical angle, which is 37 degree. So therefore from here we can say that total internal reflection will happen at P. Okay. But our IB is our 30 degree, which is less than the critical angle, which is our once again the 37 degree. Therefore total internal reflection will not happen at Q. Will not happen at Q. So it means the total internal reflection will be at P, not at Q. So this was the So it is not possible to achieve when mu is 5 by 3 and equal to B is equal to 30 degree. So reflection is going to happen at P but not at Q. So parallel going back is not possible. We come to the next question, and it was asked in the year 1986, and it states that a monochromatic light is incident on a plane surface AB between two media of refractive index n1 and n2. n2 is greater than n1 at an angle of incident theta as shown in the figure. The angle theta is infinitely greater than the critical angle for the two media, so that the total internal reflection takes place. Now, if transparent slab DEFG of uniform thickness and of refractive index n3 is introduced on the interface as shown in the figure, show that for any value of n3, all light will ultimately be reflected back again into the medium 2. Consider separately the cases when n3 is less than n1 and when n3 is greater than n1. Okay. So it means that the total internal reflection is going to take place even after the introduction of this n3. Okay. And we have to find out the two cases. So this is our figure. First, we can divide it into two parts. In the first part, it is only having a slab, and this is our medium 2 and this is our medium 1. And it is said that is incident on the surface between two media as shown in the figure. Okay. In the first case also, it will be going something like this, and the angle is given as theta. Now in the second case, a medium which is refractive index of 3 is introduced between them, and the ray is now incident at the surface between the glass as well as AB. So these are the two cases, and we have three mediums now, and it is given that a light is incident on the angle theta at the surface AB. So we can say medium 1 it is having a refractive index of n1. We have medium 2 with a refractive index of n2, and medium 3, and please keep in mind this n2 is greater than n1, and we have medium 3 which is having a refractive index of n3, and light is from medium 1. You can say light from medium 1 is incident at angle theta on interface AB, and it is also given that our so it is also given that the theta is slightly greater than the critical angle for the two media. Okay. That is our critical angle. So we are given that theta is slightly greater, then we can write it as sine inverse of n2 by n1, and this can be written as sine of theta is greater than or equal to n2 by n1 because it is slightly greater. So initially, that is without slab, we can say that the total internal reflection will take place at AB. So we can say initially, which is our without slab, total internal reflection occurs at AB, interface. Now we come to part cases. Case number A, which states that n3 is less than n1. So we have case number A, which states that our n3 is less than n1. And this, from here we can draw one conclusion that our n3 will be less than n1 and it should be also less than our n2. So therefore we can write that our n2 upon n3 is greater than our n2 upon n1, and in terms of angle we can write sine inverse of n2 by n3 is less than sine inverse of n2 by n1. So here we can make an interpretation of this result, which states that the critical angle, because total internal reflection is always dependent upon this critical angle, so we can say critical angle for second and third interface is less than critical angle for second and first interface. And since theta was already greater than the critical angle, because it is mentioned that our critical angle theta was greater than the critical angle, let me rewrite it again. Here it's mentioned that since theta is greater than critical angle for second and first interface. Okay, this was also already given in the question. It says that angle theta is infinitesimal greater than the critical angle for the two media. Okay. So based on this, we can say that the theta, or we can say it will be greater than the critical angle for the interface of medium 2 as well as medium 3. Thus, total internal reflection at B is still taking place. We can say that the total internal reflection occurs at AB, which is between second and third medium. Okay. And from here we can draw a conclusion that light reflects back to medium 2 and no light enters the slab, that is medium 3. No light enters slab, which is our medium 3. Now we come to the second case of it. Case B, and it states that our n3 is greater than n1. And from here there will be two sub cases. Okay. So we can say from here we are going to have two cases. Let us suppose this is case number 1, and under this condition our n1 is less than our n3 and it's further less than our n2. So we can interpret this particular situation, and in this case we say that our light moves from medium 2 to medium 3. Okay, so which basically means from denser to rarer medium. From denser to rarer medium. Thus we can say there is no guarantee of total internal reflection at AB because light can enter the slab. So we can say that no guarantee of total internal reflection at AB, and light can enter the slab. Okay. So therefore we can apply Snell's law. Snell's law, and it gives us that our n2 sine of theta will be equal to n3, and this is our sine of incident angle, and we can say that our sine of incident angle will be equal to n2 upon n3, and this comes as sine of theta. But we already know that sine of theta is greater than equal to n2 upon n1. So this condition we already know. Therefore we can write that our sine of I is greater than equal to, we can just modify this, we can write it as n2 by n3 multiplied by n2 upon n1, which gives us n3 upon n1. So it means we can say that our sine of I is greater than equal to n3 upon n1, and this tells us that incident angle I should be greater than our sine inverse of n3 upon n1. So it means now this inside the slab, that is a medium 3, the ray hits the second surface, which is our DE. So because now the ray enters the slab and obviously it is going to pass through the AB and hit the upper surface. Okay? It means that is it going to hit the upper surface, which is our DE. The ray is now going to hit the upper surface, and this is our AB. So we can say the ray, or we can say the light, inside the slab, which is our medium 3, hits the second surface, or the second face rather, which is our DE. And at DE, the light tries to go from medium 3rd to medium 1, because this is our medium 1 and this is our medium 2nd. So light ray will try to go into the medium 1, and the critical angle for the interface of third medium and first medium, we can write this as sine of theta prime c will be equal to n1 upon n3, and we already know that our I is greater than our theta prime c, therefore total internal reflections occur at DE. Total internal reflection occurs at DE. So thus we can draw a conclusion that ray is reflected back inside 3 and refracts to medium 2, and then refracts back to 2. Okay. So it is going to do some internal reflection and will be coming like this to the back. We will draw the final diagram at the later on. So this is approximate figure. Okay. So therefore we can say that no transmission into medium 1. And we have subcase 2, and in this condition n1 is less than n2 and is less than our n3. Okay. So here the medium 3 is denser than both medium 1 and 2. We can say our medium 3 is denser than both medium 2 and medium 1. And because of this denser, because medium 3 is denser, so we can say that light moves from second to third, it bends towards the normal, towards the normal. So once again we can use Snell's law. And it tells us that our n2 sine of theta will be equal to our n3 sine of I, and almost same calculation, we are going to get this as sine of I is equal to n2 upon n3, and this is our sine of theta, and sine of theta we already know is greater than or equal to n2 upon n1. So thus we can write that our sine of I is greater than or equal to n2 upon n3 multiplied by n2 upon n1, which gives us n3 upon n1. So it means our angle of incidence is greater than sine inverse of n3 upon n1. So it means when reaching DE, the incident angle inside 3 is slightly greater than the critical angle at the interface third and first. So from here we can say that when reaching DE, the incident angle inside 3, that is inside medium 3, is slightly greater than critical angle, greater than critical angle at third and first. So therefore total internal reflection occurs at DE. And once again ray is reflected inside 2 and refracts back to medium 2. Sorry, it has to be 3 here. So in both the cases, sub-cases rather, case 1 and case 2, no light enters medium 1. You can say that in both cases no light enters medium 1 and all the light is reflected back to medium 2. Okay. All light is reflected back to medium 2. It would be either directly from surface AB or bouncing back from surface DE. So we can draw an approximate figure for that, and so we are having this is AB and we are having a surface, this will be over CD. So this is our medium 1, we have medium 3 and medium 2, and Let us suppose this is point P. A ray of light is incident at angle of theta here, and in this case, in the first case, it is going to bend away from the normal and something like this. Sorry. And strike here and like this. So this is the angle of incident and this will be the angle of incident. And for case B, same situation, but only thing is that the ray will be bending in the opposite direction now. So this is 1, this is 3, and this is our 2. So this is our AB and this is our CD, and this is point P. So the light ray is at angle of theta and it will be bending something like this, and once again this will be angle of incident here and this will be angle of incident here. Now if we combine both these figures, we can just draw a rough approximation of the combination because of the total internal reflection, especially at the slab. So this is a glass slab, and this will be angle of theta, and it will be bending like this. Sorry, normal and internal reflection, and once back to this. Okay. So this is our glass slab, and we have this as 𝑫𝑬𝑭𝑮, this as 𝑫𝑬3, and this will be our 𝑫𝑬2. So this is the total internal reflection, and yes, so this was our AB and DE. DE, or sorry, it has to be DE, my mistake. So this has to be our DE, and here also it has to be DE. So this is our DE, and yeah, so this was the last one. Yeah, so these were the questions that was asked in the year 1986, 87, 88 and 89. So a total of 7 questions. So this completes all the 7 questions. Thank you.